Hello everyone, my name is Nguyen Hoang Khoi. Today I would like to present my research that is a tightly coupled visual-inertial system with synchronized time for indoor localization. The first problem of indoor localizations is that the GPS signals is not available because it had been blocked by the building's material. One solution is using laser scanners or LiDAR. However, 3D LiDAR usually is very expensive and not affordable by normal users. On the other hand, cameras are more popular and have been employed on mobile robots for supervising purpose. So it will be a great advantage if we can use this camera for localization. This approach has been researched and known as visual odometry. However, the main drawback of visual odometry is the low update rate of computation and the low frame rate of camera itself. This makes pure visual odometry system hard to catch fast and dynamic motions. In this research, we are going to integrate the camera with inertial measurement unit or IMU to increase the system update rate as well as improve the observability of the system on dynamic motion. We choose the tightly coupling scheme which account for the internal relationships between sensors. The contrast is loosely coupling, which only combines the output of each sensor module separately. Apparently, the tightly coupling system is more precise, but it comes with the price that we have to accurately synchronize and calibrate the sensors. To perform the time synchronization, we first program the IMU board to generate a periodic pull signals to externally trigger the camera. We calculate the sensor's timeline difference DL and timestamp difference DS by measuring the time delay terms, such as communication delay TD1, IMU filter delay TD2, and camera shutter delay T-shutter. From that, we derive the suitable delay T-jig to add on the trigger pulse to exactly synchronize the IMU and camera data, where TA is the aligning offset. The sensor calibration is divided into two steps. In the camera-to-camera step, we find each camera intrinsic model H1 and H2, as well as the extrinsic transformation TC1, C2 of the stereo setup. After that, the second calibration have us find the camera to IMU transformation TC1I. To collect the dataset for the camera to IMU calibration, we move the sensor in front of a calibration pattern, in this case an apple grid. As shown in the video, the motion should be smooth and excites on the IMU translations and rotation axis to obtain a good calibration. Finally, the calibration is calculated by using the Calib toolbox of ETH University, which is available online. From the synchronized and calibrate system, we estimate the robot's motions using the Visual-Inertial Odometry or VIO algorithm. The estimation processing is called the back end to distinguish with the image processing program, the front end, which we will talk about later. First, let's X denotes the state vectors of robot, including the robot's positions, orientations, and velocity, as well as devices of gyroscope and accelerometers in the IMU. On each IMU cycle, the state vectors is predicted by propagating the IMU model with IMU measurements. Meanwhile, the state update is conducted on each camera cycle, where the image reprojection errors and the IMU errors are jointly minimized in a nonlinear batch optimization. The front end owns the functions of extracting 3D landmarks from images to supply for the back-end update. The playing videos visualize the operations of the front end with the most recent keyframes on the above and the current frames on the below. First, 2D key points are extracted using the bridge feature detector. Given the propagated state from IMU measurement, the front end considers the previous landmarks that could be visible in the current frames for 3D to 2D matching, which is marked with green lines on the video. Next, the 2D to 2D matching, which is marked with yellow lines, is performed across all images. Potential landmarks will go through a ransack step to remove outliers, and only qualified landmarks are transferred to the optimization. New keyframes is selected by a heuristic rules that helps the landmarks to be viewed from different angles. Finally, the process windows is marginalized out to ensure a limited number of most current frames and previous keyframe. For the implementation, we build the system hardware with a Bumblebee stereo camera, an analog device IMU, and an industrial embedded computer, which is small size for easy deployment on mobile robots, but still able to process the VIO algorithm in real time. The hardware system is compacted in an 18 by 16.5 by 12 centimeters box. Also, we program the system software on the robot operating system, ROS, for a concrete platform while using the C++ language for high-speed performance. In the slider experiment, we tested the VIO system on a single forward-backward motion generated by a custom-made linear slider, as shown in the video. The motion was created in form of a sine wave of 0.5 Hz on the trajectories of 60 centimeters. The encoder was used a crowd-truth position to evaluate the VIO estimation output. The dataset lasts about 6 minutes. The system estimate positions is shown on the figures. The translations and orientation errors of the VIO system were measured statistically and expressed in relation to the travel distance. After 110 meters travel, the translation errors is below 10 centimeters. Yaw errors is below 0.5 degrees. In order to evaluate the system on real-world motion, we conducted the experiment of carrying the system and walking around the room in loops. The trajectories were round on the floor as a 6 by 3 meters rectangle with 0.6 meter turning radius. The total path passed 11 loops in 5 minutes. We can see the estimate trajectory was very similar to the design one. Since there was no available ground truth data, we calculate the repeating error each time the system went back to the beginning point. We run the algorithm repeatedly to obtain the statistical expressions of the errors. After over 200 meters, the translation errors were kept below 0.5% of travel distance, while yaw error will remain smaller than 0.1 degrees per meter. In this research, we have presented a tightly coupled visual-inertial system that works in indoor environments. Experimental results have shown the high accuracies of the system in real-time performance. This system could be extended to work on other GPS-denied environments, such as dense urban areas or underground mines. The presentation is finished. Thanks for watching.